Hey there, folks. This video is the third example in a series of 3 example problems using our energy equations, our mathematical models, to make predictions or to say what's going to happen in this particular scenario. So here is example 3. Your cousin Throckmorton kicks a 2.75 kilogram box. After the kick, it has an initial speed of 8.50 meters per second. The box slides across a rough surface until it comes to rest after sliding 2.45 meters. What is the strength of the friction interaction between the box and the ground while it slides? So there's our question. I first want to point out that if you're using the handout that I gave you, an early version of this anyways, I left the mass of the box out, but you do need to know that. This box is 2.75 kilograms. So that information, you should add it in if you're following along with the handout that is missing the mass. This example is here because the previous 2 examples had a lot of like step by step. Here's what you do first, here's what you do second, parts A, B, C, D, and this is just a question. But I want to highlight that even when it's just a question, you really ought to be doing the things in the first 2 examples. So even though it's not prompting you to do so, you really should sketch the scenario. So I drew a picture of what was going on. I drew a moment A where the box already was kicked by Throckmorton, and a moment B where it came to rest. I annotated with the distances, the speeds, the mass of the box. Nowhere in this problem does it say draw an energy bar chart, but really to think through what's going on, my brain needs an energy bar chart. So I'm going to draw one. It wasn't given to me. I'll sketch my own rough one. It might look something like this. I draw LOL for the 2 bar graphs in the system in between, put all of our energy accounts on the bottom. Now I'm going to start thinking about my system. I think, maybe the box, the surface, the gravitational field of the Earth, and Throckmorton might all be helpful, but actually, wait a minute. There's no height changes, so the gravitational field of the Earth is not a giver or receiver of energy. And Throckmorton kicked the box before my chosen moment A. I chose moment A to be the moment after the kick because I knew how fast the box was going after the kick. And so, really, I don't need either of those because Throckmorton did give energy to the box, but before moment A. And the gravitational field is never a giver or receiver of energy in this scenario. So now let's go through our bar graphs. The box is already moving at moment A. No height changes, no elastic energy changes, no thermal energy, and chemical energy we don't need to worry about because Throckmorton finished kicking the box before moment A. What about moment B? I drew something like this where the box slid, there was a rough surface, there was friction involved, so it all became thermal energy, which is why the box stopped moving. No height changes, no elastic energy changes. And so I'm going to write my energy conservation equation as something like the kinetic energy at moment A is equal to the thermal energy at moment B. Cool. Didn't prompt for that in the question, but it's still important to do those steps to reason through what's going on. Always, always, always sketch yourself an energy bar graph if we're using energy to model a scenario. And always draw a picture. The picture is so helpful. All right. With that, I'm going to make a list of the information that I've been given, the information I want to find. It's helpful to organize myself in that way. I know that the mass of the box is 2.75 kilograms. I know that the speed at moment A is 8.50 meters per second. And I know that the distance the box has traveled by moment B is 2.45 meters. Now I know I'm trying to find the strength of the friction interaction, which is abbreviated lowercase f. So there we go. That's what I'm trying to do. Let's go ahead and solve some problems. And of course, we are going to start by writing a general equation. That equation will be the energy conservation equation that came from the bar graph. The kinetic energy at moment A equals the thermal energy at moment B. You already know I'm going to expand this out into relevant energy relevant energy equations. Kinetic energy is half times mass times speed squared. Thermal energy is the strength of the friction interaction times the distance traveled. The speed at moment A has a subscript A to annotate that. The distance traveled by moment B has a subscript B to annotate that. And I'll be color coding. Kinetic energy stuff is blue. Thermal energy stuff is green. What's my find? My find here is the friction interaction. I only have 2 terms, so I don't need to worry about addition or subtraction. All I got to do is divide the distance here so that the friction is by itself. If I divide both sides by the distance traveled by moment B, I notice, or by doing that, I get that the distance on the right divides to 1, and I'm left with the mass times the speed squared over twice the distance is equal to the friction. I want to point out a quick math trick I did there. I had a half mv squared in the numerator here. A half in the numerator of a bigger fraction is the same thing as just having this 2 in the denominator. So this blue 2 corresponds to this blue 1/2 there. Try it out for yourself. If you don't believe, plug in some numbers, see if it works out. Cool. Now wait, is that it? Is that all I have to do? The thing I want to find is by itself. The other side of my equation, mass, speed at A, and distance at B are all in my given information. So I have indeed written my find in terms of the givens, which means I'm finally ready for step 3, plugging in numbers. I've moved the friction to the left side of the equal sign, the friction, or the strength of the friction interaction, that is. The right side of the equal sign has the mass of 2.75 kilograms, that speed of 8.5 meters per second, all squared. The denominator has that exact number 2. Excuse me. And the distance traveled at B of 2.45 meters. I'm going to grab my handy dandy scientific graphing calculator here from Desmos. On the left is what I plugged in. I made it look exactly like the stuff on the right without the units. When I do that, I get 40.548467, blah, 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 as my number. Everything in this expression is either exact or has 3 sig figs, so I'm going to round to 3 significant figures for the strength of my friction interaction, getting 40.5 joules per meter. Meaning for the strength of this interaction means that for every meter this box travels, 40.5 joules of energy will transfer into the thermal energy account. This is my pitch again. Get yourself a fancy calculator that can type things in all at once that looks like this. It makes it easy. If you're using a more simple calculator, you have to be more intelligent and you have to use order of operations properly. Cool. I think I'm good. I want to make sure I've got the correct units here. Let's do a quick unit check. My units look like this. I have a kilograms coming from the mass. I have a meters per second all squared coming from the speed squared, divided by a meters coming from the distance, and then 2 is unitless. So my units look something like this. I stare at that and say, wait a minute, a kilogram multiplied by a meter per second quantity squared, that's the definition of a joule. And so I just replace that numerator with a J, and I've got joules per meter, which is indeed the unit for the strength of a friction interaction. That's it. I did it. Great. So moral of the story here is you should always draw a picture. You should always do a bar graph, even when not prompted, and everything else is the same. Make out a list of givens and finds, isolate your find based on what's given, plug in numbers, solve, check your units. Thanks for watching, folks. Let me know what questions you have.